It was off. But
voice is so clear.
that's okay. No, it's not. Well, okay, you can do it indeed on a massless limit, but then you make Lorentz invariance very non-manifest. But okay, yes, let's. So this massless limit is not reality. So as I say next, so there's a problem. Okay. So there is only some approximate cancellation, and in particular, we cannot really do a useful field redefinition. So our effective field theory, and moreover, mass of the axion is of order the string tension. Okay, and our effective theory breaks down at energies bigger than this. So is it even a sensible limit in any sense, or am I just doing some pure numerology? Okay, so to support that it's not pure numerology, let me explain to you some results, some updates, some old and new results on worldsheet S matrix boost. Okay, so punchline is the following: the older result of this very nice paper is that Bootstrap also finds the axion of comparable mass, and with coupling also very close to this critical coupling. Okay, and then update is that this physical mass of the axion is light. Okay, to the extent that Bootstrap results do not change much if we take MA to 0. Okay, so it's some way of making kind of Bootstrap, I'd say, is a bit more rigorous way of doing some naive dimensional analysis, putting some factors of 2pi in the place and saying that this mass is actually a light particle. Okay, even though naively it doesn't seem so. I'll explain in a moment. Yeah. Okay, that was punchline. I mean, then now let me say what I mean by this phrase. Okay, just to tell you what you should anticipate on this discussion. Okay, so we use effective action without. So what does Bootstrap do? So we use effective action without axion. Okay, so axion is not put in, but with some non-universal terms included with like arbitrary coefficient. Okay. So first on universal terms, and Bootstrap studies 2-to-2 scattering. So then the amplitude leading corrections to the amplitude are parameterized by these numbers alpha 3 and beta 3. For example, the log of the amplitude in anti-symmetric channel, it depends. Okay, that's the leading piece. That's the one loop piece. Remember, this alpha 2 is this d minus 26 term. And then that's what related to particle production, but it's its avatar in the 2-to-2 amplitude. And then there is some combination of alpha 3 and beta 3 that appears at next one. So then what Bootstrap does, they use crossing and unitarity to constrain alpha 3 and beta 3, and then okay, look close to the boundary. So this look close to the boundary thing is in green because constraints are rigorous, but the idea that you need to look close to the boundary, that is a little bit inspired by some success of conformal Bootstrap, etc., where you find some physical theories on the boundary. So we can discuss how to justify it, but for now let's just do it. Okay, and that is what's happening. So I'll guide you a little bit through this plot. So you see this is this alpha 3 beta 3 plane. So everything in white is excluded. So theory must live in this gray region, and that is rigorous. So now there are two boundaries. Okay, and if we look at the boundary where beta 3 is positive, then there is one sharp resonance. Okay, and now we look near the boundaries. So near that boundary is one sharp resonance, who is a pseudoscalar, so it has the quantum numbers of the axion. And here, as we move along this boundary, the mass of this guy moves. You see the color coding from blue to red, it moves from blue to red, and then like 1.5. Okay, that's somewhere here, so it belongs to the plot. And moreover, now if we look at the coupling, then coupling for all this range of masses, and especially when we go to mass something like 1.5, it almost is not changing. Okay, it's converged to this value, and this dashed line is that critical coupling. Okay, so these are the numerical results, and this is what I mean, that MA corresponds to MA 1.5 already corresponds to large beta 3, because from the point that corresponds to this mass to beta 3 going to infinity, pattern of resonances and say couplings of this resonance basically does not change. Okay, so in this sense, Bootstrap already converged to a massless MA limit then we take the physical mass, right? So that's sort of Bootstrap allows us to study some theories that are not QCD, you know, some, I mean, just maybe non-physical theories, but okay, they capture some infinite set of dispersion relations, right? So that is the point. So it's not just random non-physical theories. Good, and that basically then, as I show on the next slide, but what we did, we developed some scaling theory that tells us that the here physical value of beta 3, whatever, what appears in computation is some combination of beta 3 that even, you know, here like beta 3 is small, but really what appears in the counting is this combination, which is of order 20 for this value of beta 3 corresponding to MA. So you get some 5-ish% results within the massless axion limit. Okay, just very quickly because okay, I'm running out of time. So these results can be understood by using like a scaling theory of light axion, where basically all non-universal corrections of the action are dominated by integrating out the axion. And more or less this what Bootstrap finds. Okay, and that will be justified if the axion was very light. Yeah, maybe. Okay, Andrea there is nodding approvingly, so he understands this much better. But yes, and as I said, so precise cancellation, and then so this cancellation of here we studied just 2 to 2, but there is a cancellation of 2 to 4 related to the cancellation of growth in the 2 to 2 amplitude. Okay, and then this precise cancellation Bootstrap finds only in beta 3 to infinity limit, but okay, for this value of beta 3 that we care about. And beta 3 is just related to the mass by some simple scaling formula. It already this happens. Okay, so sort of numerology got confirmed by Bootstrap, and the justification for light axion limit was also provided by Bootstrap. Okay, now let me review very quickly the BFKL. I'll probably skip Regge theory. So we would like, what's the point? We would like to UV complete the broadsheet effective theory by matching it to high-energy QCD. So that's the big goal. So now Regge's theory is one potential way to set up such a connection. So let's consider high-energy scattering in QCD. So I'm taking the following order of limits. So as I said, n is the largest here, s I take large, much bigger than minus t, but t itself is 6, but bigger than lambda QCD. So in this limit, amplitude is given by a sum over some s to some power laws that depend on t. So these guys are the Regge trajectories. Okay. So now BFKL and some further developments is a tool to determine this alpha ends of t, and it is really controlled when the t is absolute value of t is larger than the QCD. So I'll just give you here the answer that these alpha ends are given by eigenvalues of certain differential, whatever, integral operator that acts on functions of R variables. Okay, where of these R variables, we can think of the positions of so-called regions. There are some regions that are represented by these blue lines, and they live on two-dimensional planes. And then there is some operator that we need to diagonalize on this basis of functions of R variables, and that will give this set of Regge trajectories. So say leading order in lambda QCD that is small because I'm at large S and large T. This operator is given by a sum of pairwise interactions, where each pairwise interaction is this sort of relatively simple looking kernel. Okay, so that thing starts looking, especially in the limit of large number of regions, as some sort of spin chain, where at leading order we just have to nearest neighbor interactions, but then at high order some more complicated interactions appear, and also this kernel gets modified. In the regime where we have control, so that Hopf coupling is small, and again we're at large n, you see that this say the ground state of R equal to operator, that's what's called the Pomeroy trajectory, that's the leading Regge asymptotics in this region is given by this formula, where you see something interesting happens, that subleading correction there's a leading answer. The subleading correction is also computed, is proportional to the beta function. And it so happens that this leading kernel, it turns out to be an integrable system as well. But then the subleading correction, it breaks integrability. And note that there is also this thing that was mentioned in the talks just before, that this coefficient is, some 11 over 3, and you can add some, flavors to the theory. It will change in this form. It's the same coefficient as breaks integrability in our low energy stringy picture. So the hope here is that, okay, and this axion almost unitarized this particle production in the string picture. So the hope here is that, okay, maybe we can match our IR calculation to this UV calculation, okay, staying within a single string sector, because we're at large N and physics is, closed. Very single string sector, and that's what I say here. Could this be connected to UV integrability? This approximate integrability of BFKL, connected to this integrability of strings. So I remind you my big picture. So here we have T. Here we have the region of long rotating strings, and here we have BFKL. Okay, so according to Regge theory, these are connected by continuous Regge trajectories, and if alpha of t is analytic function, can we connect the two? Now, how much time do I have? 5 minutes. Okay, so I wanted to discuss a little bit, review the Regge theory, but okay, it's not worth in such a short amount of time. Basically, an argument for why. You see, it's a non-trivial statement, right? It's not a trivial statement that positions of physical particles in T-channel scattering are connected to the asymptotics in the Regge limit, right? But that is, at least for a meromorphic amplitude with which we're dealing here, it can be established, okay, modulo some subtractions, assumptions about UV behavior, but that's what I wanted to review here, but I guess anyone can read Gribov's book. Sorry. Yeah, yes. You can read in Russian too. So. It's even better. So again, yes. So the punchline is that there is, I think, a justification for continuity of this Regge trajectories. There is a regime where we have control by using long rotating strings. So what I reviewed to you was the theory of long strings of type 1 and 2. But as also Gabriel mentioned, the bulk of the string of this long rotating string is the same. As Arkady was asking, whether the worldsheet theory is the same. So there is also some approximate integrability that is related to this long rotating strings. Now, when T becomes small, string becomes shorter. We lose control. This blue region is we don't have control, and then there is a green region where we again have control, and we have this spin chain that is also integrable and kind of becomes non-integrable and strongly coupled when we go here. Yeah, these guys are Jezide gluons, these blue lines. Yeah. I'm skipping this derivation because it's complicated, the Romania, but okay. So now, yeah, basically what I want to say, a real QCD trajectory, that is this red line that becomes something wiggly, maybe complicated here in the middle. Okay, but what we are looking for is some integrable approximation, okay, some imaginary integrable theory. That's this purple trajectory that matches well to real QCD, I mean, still large N, whatever, in this region. And that matches well to BFKL in this region, okay? And then we've seen some hints that these deviations from integrability, they are small and maybe even sort of smaller than expected by naive power counting in this region, right? That is what I reviewed in the beginning of the talk. Okay, good. So yeah, that is what I just said, and then we need to understand this approximate integrability for rotating strings. But it is something concrete that we can do, and what Gabriel and friends are working on. What I want to say is that also we have, I'm concluding basically. So it's good thing that we have ways to test how robust is this numerology of ours, these constellations, right? Because, for example, we can study theories with additional matter, right? And then we know how matter changes beta function, and if this axion coupling survives the integrability condition. And we also study theories in smaller dimensions, say this BFKL machinery can also be developed in 3 and 2 dimensions. And then this maybe will be even simpler examples where we can make some analytic progress. Okay, so using both lattice and analytic constellation. And then, my last slide is that, of course, the Regge limit is just, it's one of possible connections to of long strings to QCD. For example, if you remember Raju's talk, so he talked more about some quarks or whatever partons flying apart and emitting soft gluons in the middle. And then, so this, the distribution of very soft gluons over here at large n should also be described by the theory of long strings. So this kind of production of a string more in S channel, but this is a real string, while this BFKL is supposed to produce some sort of analytically continued string to negative energies. So anyway, this is what we're up to. So I'm hoping to report on the progress of this computations that we're doing in the future meetings. Thank you for. Well, yeah, we try to establish.
I remember it went down about the effect of this task.
Yeah.
Even heard from some people that it might change the slope. It's gone away.
Well, I don't think, again, from effective theory, they cannot change the slope. They can give this correction that is j to 1/4 as opposed to linear j, so it's relative to j to the minus 3/4. But on the other hand, I should also maybe mention that there is some puzzle in 3 dimensions when we look at the lattice data. So there is a spectrum of glue balls. They seem to lie on a very linear trajectory, but the slope of that trajectory does not match this tension, that you would derive from effective string theory. So it is a puzzle. I don't know. I think it's very interesting to understand whether it is some lattice an artifact or it is something important that we're missing in this effective string theory. I don't think it can be, fundamentally wrong, but okay, maybe there is some big ingredient that we're missing, and that's something again that would be very surprising. But I think we have the tools to debug it, using lattice. We can more, I think, in principle, understand sort of the shape of these objects, and we can see, spend 6 glue ball, for example, how it looks on the lattice. You can more or less study it and see, what's wrong or what's right. So yeah, it would be surprising, but also interesting if something is wrong with that picture at a basic level, right?
There, on the other hand, very precise match quantum numbers, basically all of those people to the speech interpretation string. All of those people, to each of them, can be just identified with participation. But then they slow the linear trajectory from get 20% off. It is very hard. So I think there is some idea.
No, you told me some arguments why the cap may generate non-local terms.
So that I hope that maybe that was my calculation to start with because it's very slow.
Yeah, in principle, just to sort of speculate on if this works, then okay, this BFKL chain, there are some boundary conditions. So you create something that looks like an open thing, even though that's supposed to match to this group. So you should sort of recognize that there's some left moving and right moving sectors. And in principle, there is, there are some boundary effects over here. But yeah. Mm-hmm. I skimmed over it because I don't think there is an argument, and moreover, I'm not committing at all, to be honest, that the leading trajectory over here maps to leading trajectory over here. There are in principle even some reasons to believe that I think there are reasons to believe that at large n there will be some level crossings among these trajectories, and it is sort of the part of the problem is to actually identify. So here we have good control about a bunch of leading rigid trajectories. Not to complicate the picture, I drew them without any crossings because it's not something I'm certain about. But I'm not making a claim that it's really the pomeron that is continuously connected to the leading global spectrum. It would be true if there were no level crossings. But I think at large n, at infinite n, in the strict planar limit, we can actually expect some level crossings in this picture for some subtle reasons that we can discuss. So yeah, I'm not. This is very schematic. These points are put like at random. Okay. Lattice global is a scalar that we know from the date from lattice, yes. So that in 4D and in 3D that happens to be the case, but there isn't, I think, a theoretical really arguments. Yeah.
I have a question. Can you imagine that if you change the matter content, you could make the lightest state?
Yeah, that is. I think it's really interesting to, again, the only way I know how to address this is lattice. Yeah, I don't know, maybe in particular in supersymmetric, Yang-Mills. Yeah, in supersymmetric there should be some degeneracies, but okay, I think it's an interesting question. What happens if we add to our action, some adjoint fermions and some adjoint scalars? And
well, particularly,
mm-hmm.
Or you can get both of them.
So why is that? Why you get pseudoscalars?
So they're not pseudoscalars. Well, just because they're Carlson.
Yeah, but pions. Okay, good. I'm not sure if pions. So here it's true. We should see pions on this plot, but I do not know, for example, how this will manifest itself on the string world sheet. I think that's an interesting question. Like, do we see anything special on the string world sheet if we have, let's say, some chiral symmetry break?
The model of Thomas. Yeah, the Thomas model has CP1. Yeah, but I'm saying the cap response is about so.
Yeah, you see, if it, yeah. Well, at large n, the point is that at large n they decouple. Yeah, I think that will not invalidate the argument. But whether you get some, sometimes people propose some interesting sigma models on the world sheet, but that, of course, you expect it to get gapped because it's two-dimensional theory, okay, some 2D sigma model. But I mean, in supersymmetric theory, of course, we expect some Galstinas on the world sheet. That's a very sharp prediction. Then if we have, some fermions that are massive by light, you expect some light fermions. Okay, if you have some scalars in the bulk, you also expect the scalars to incorporate into the string. That's what I meant by this light comment. So you can tune and produce some other light scalars on the string, and they will run in this loop. And you can see if our formula for the axion coupling, if it follows the same pattern as the beta function, right? So I had this this formula, and if we add some scalars, they add to this -5, right? And then the question if the logic continues to hold.
Time for everyone. I would say very inspiring meeting. I think it's a good start for our series.